let's just start with proving an interesting lemma which kind of relates the relationship between the algebraic multiplicity and the geometric multiplicity of an eigenvalue actually. So let A is a square matrix and lambda is an eigenvalue of the matrix A. Then here's the interesting conclusion. Geometric multiplicity of the lambda is always less than or equal to the algebraic multiplicity of the lambda. Okay? Then the geometric multiplicity of the eigenvalue lambda is equal to the algebraic multiplicity of the lambda. So this is what that I would like to use. Okay? The proof is a bit involved. It's not difficult actually, but you have to be a little bit patient. So the proof goes like this actually. What is the geometric multiplicity associated with lambda? So the geometric multiplicity of the eigenvalue lambda is the dimension of the eigenspace of the matrix A, which is same as the dimension of the null space of the operator A minus lambda I actually. Okay, so it's equal to the dimension of the null space of A minus lambda I. Let's call this eigenspace, let's give it a name V lambda. Okay. So V lambda is the eigenspace of A actually. Now what we can do, so since this is a subspace of Fn, so for sure this is a subspace of Fn. So what you can do, you can find an orthonormal complement of it actually. Okay. So let W is a orthogonal complement. Okay. Complement of V. That is W is V lambda perp actually. Okay. So I know that I can write Fn as the eigenspace E lambda, V lambda plus the direct sum of V lambda and W, which is the orthogonal perp of, so W is the orthogonal perp of V lambda actually. Okay, this is what that quick result that you're gonna get. Next is, so Fn is finite dimensional, V lambda is finite dimensional, and the dimension of it is G lambda. Okay. So what are the dimension of this V lambda? So it's G lambda, and what would be the dimension of W? So it's going to be N minus G lambda. Okay. So let's assume that there are vectors say U1, U2 up to U G lambda. So this is the index G lambda. Okay. That is the basis for V lambda. Okay. Let's call that, this is the basis for V lambda. And say, let's, for the sake of simplicity, let's give this G lambda a number M actually. So let's call this M. The M is G lambda. So, and let's assume that Um plus 1 up to Um plus 2 up to Un is basis for W actually. And obviously when you put together all this is going to be the basis of Fn. Okay? It's going to be the basis of Fn. Now I want what? Let's apply the A onto say these vectors first and these vectors first. by applying the A onto these two vectors, I want to find a fundamental form of what do you call the matrix A actually. Okay, so I want to have a fundamental structure of the matrix A, that how does this matrix A looks like actually. Okay, how does this matrix A looks like? So for example, if you take A and operate it on UI, okay, and UI is an element of the eigenspace of lambda. By the way, what is the explicit definition of eigenspace of matrix A? So it's a collection of the vectors U from Fn or V from Fn such that a V equal to lambda V. So this is what it is. Now UIs are basis for V lambda. So these are the vectors in basis V lambda actually. So if you're gonna put this, let's put 1 for example. If you're gonna apply A onto U1, and U1 is an element in V lambda, so by definition this must be equal to what? Lambda 1 U1. Okay, so this is going to be equal to lambda 1 U1. I want to rewrite this expression in this manner. Let's say that this is equal to A11 U1 plus A11 U2 plus so on and so forth A11 UN. In other words, I am 1n UN. I'm expressing this AU1 in the terms of the entire basis actually. Okay, the entire basis. Where A11 is this lambda and rest are 0. They all are 0. They are 0 actually. Okay. This is A11, A12, A1n, so this is equal to 0. How about if I'm going to apply A onto U2? I'm going to get lambda to U2, but I can play the same game with it. I can say that you're going to have A21 U1 plus A22 U2 plus so on and so forth A2n and UN. Okay, A2n and UN, where A21 is 0, A22 is lambda, and rest of the coefficients are 0. So this is going to be equal to lambda to U2. So I'm not changing anything chemically, so I'm just changing things physically actually. So this is going to be AU2. So finally, what would be AUM actually? How does the AUM is going to look like if you keep on doing it? Okay. So I'm just writing it explicitly so that you can see everything. The AUM is going to be a matrix like, it's going to be a vector like, okay, A1M, U1 plus A2M, UM, U2 plus so on and so forth. A term will appear like, okay, this is going to be A1M, A2M, yes, AMM, UM plus so on and so forth, A and M actually. Okay? A and M. Am I writing the index correctly? No, I'm not writing the indexes correctly. So this is going to be AM1 U1 plus AM2 U2 plus so on and so forth. A term will appear AMM UM plus so on and so forth, and AMN UN. This is what it is going to be. So now we are done with, and obviously this is 0, this is 0, this is lambda m, okay, this is lambda m, this is lambda 2 here, this is lambda m, and rest are 0, okay, because AUM, this AUM is equal to lambda m UM. This is what that you're going to get. So both sides are equal. How about AUM plus 1? Now these are not the eigenvectors of what do you call A actually. These are not the eigenvectors of A. They are not the element of B. So you're going to get some coefficient actually. Okay, you're going to get some coefficient for it actually. So in other words, AUM plus 1 is an element in Fn, and you can again write them as a linear combination of these vectors. So let's say that these are AM plus 1, 1, U1 plus AM plus 1, and 2, U2 plus so on and so forth, and AM plus 1, N, and UN. And similarly, the last one, which is going to be AUN, is going to be AN1, U1, AN2, U2, up to so on and so forth, ANN, and UN. So these are the going vectors. These are not necessarily zeros actually. These are not necessarily zeros. Now, if you're going to compare them, these coefficients, with the entries in A actually. So in other words, if you put together all these coefficients, in other words, A11, A12 up to A1n, and A21, A22 up to A2n, and AM1, okay, AM1, AM2 up to AMN, and so on and so forth, AN1, AN2 up to ANN actually. So if you write it in this manner, you can also write this as, you can write this as a transpose actually. In other words, you can put these vectors in columns, doesn't matter. Okay? So this transpose must be equal to the A. This must be equal to the A, keeping in view this description of matrix A actually. Now, if I, for example, substitute these values, so I'm taking a lot of time. I could have written this directly, but I want that you should realize that where everything is coming from actually. Okay? What this first row is going to look like if you write it explicitly. So if you write it explicitly, the first row is going to look like lambda 0, 0, 0. Okay? The second row is going to be 0, lambda up to 0 because, because of, the assumptions, not assumptions, but because of the description of the vectors. Okay? And the nth row is going to be 0, 0, and lambda would come somewhere in between on nth position, and you're going to get to 0. And the rest of what you call the rows are not necessarily zeros actually. So you're going to get, say, AM plus 1, 1, 1, AM plus 2, 2, up to AM plus 1, n, up to the final row is going to be AN1, AN2 up to ANN actually. So this is what that you're going to get. Now let me write this in the block matrix form actually. Okay? In the block matrix form. So what would be the block matrix form of this matrix? So if you treat, for example, this block up to M as one matrix and all of these are zeros, so this matrix can be written as lambda I, where I is identity matrix. I'll write in a moment its order. And this is a zero matrix. And you can put similarly these two matrices in the form of some matrix, say, I don't know, let's call it B and let's call it C actually, it doesn't matter. Okay? Let's call it B and let's call it C. Now, what is the order of the identity matrix? The order of identity matrix is M by N. Okay? The order of this matrix B is M by N minus M. Okay? And this matrix has an order. So the order of B is m by n minus m, and the order of C is n minus m by n minus m, okay, where m is the geometric multiplicity, keep in view. So these are the orders of it actually. So similarly, you're going to have the order for A. So I'm correct actually. So in other words, that's how the matrix A is going to look like in block form. Okay, that's how the matrix A is going to look like. So if A has, so what does this conclusion is telling you? This conclusion is telling you if A has a matrix and say an eigenvalue and with some geometric multiplicity G lambda, the fundamental structure of A should be something like this actually. Okay, something like this. Maybe you need to put a transpose here. Okay, it's going to be something like this. So, what I'm interested in. Now let's compute the characteristic polynomial of A. So for computing the characteristic polynomial of A, okay, I can say that let's compute xi minus A actually. Okay, and let's assume that the matrix I is an n by n matrix I. So I can write this as that you have an m by m matrix here, 0, 0, and an n by n minus m by n minus n minus m by n minus m matrix A. So n by n matrix A can be also written in the two block matrices format. So once you're gonna get this, okay. So if you have this matrix, then that you take xi and subtract it from A, so what you're gonna get? You're gonna get lambda im minus xim, and this is going to be negative b, this is going to be 0, this is going to be xi, okay, identity n minus, so this I is basically this identity matrix, I'm just keeping it I actually, minus C actually, okay. So I mean, if you wish, you can put the order m minus n by m minus n matrix, doesn't matter. This is what that you're going to get. Once you're going to get this, keep in view what we want to do. We want to prove that the geometric multiplicity is less than or equal to the algebraic multiplicity. Okay, this is what my the major concern is. But getting into the theorem kind of also gives you a realization that if A has an eigenvalue with the geometric multiplicity G lambda, A has such a structure actually, must have such a structure. So the proof also reveals something fundamental about A actually. So what would be now the characteristic polynomial of matrix A? So it's going to be the determinant of xi minus A, which is going to be simply the product of these two. In other words, the determinant of x minus lambda times im multiplied by the determinant of C or xi minus C actually, where I has that order that is mentioned there actually. Okay. Now, what is this quantity? I'm interested in only this quantity. Okay, this is some polynomial. Okay, this is some polynomial. What is this identity? So the x minus lambda multiplied with the identity matrix of order m. So how does it going to look like? X minus lambda 0, x minus lambda, and so on and so forth, x minus lambda. So it's an m by m matrix. It's an m by m matrix where you have zeros here and zeros here actually. So what would be the determinant of this matrix? The determinant of this matrix is going to be the determinant of this matrix, okay, is going to be what? Is going to be x minus lambda power m, okay, times this actually, okay. I don't know, let's call it some polynomial p of x. Okay. let's call it some polynomial p of x. So in other words, the characteristic polynomial of a matrix A whose lambda is eigenvalue and m is its geometric multiplicity is going to have a characteristic polynomial, is going to have a term of this form actually. But what does this shows? So this expression shows that this x minus lambda power m divides the PA of x. Okay? It divides the characteristic polynomial of A. And if it divides the characteristic polynomial of A, by the way, the lambda also going to have some algebraic multiplicity. What is going to be the algebraic multiplicity? How does that algebraic multiplicity is going to appear in the term? So it's going to appear in the term as x minus lambda power some algebraic multiplicity A lambda, okay, times q of x, what do you call times q of x. Now x minus lambda power m is dividing such an expression. If it is dividing such an expression, that means that x minus lambda power m divides x power x minus lambda power a lambda. Now this division is only possible if this m is less than or equal to a lambda, and this m is really the geometric multiplicity. Okay, so this m is really the geometric multiplicity. So what does this result show? That for any given matrix, any given eigenvalue, the geometric multiplicity of the eigenvalue is always less than or equal to the algebraic multiplicity. This is true in general. Now, let's move to another interesting lemma, which is going to play a crucial role in diagonalization. Studying the theorems about, the basic theorems about diagonalization. It says that what if the algebraic multiplicity is equal to the geometric multiplicity? In other words, I know that geometric multiplicity is less than or equal to algebraic multiplicity, but imagine you have a matrix in which every eigenvalue, okay, has algebraic multiplicity equal to the geometric multiplicity. Okay, so you have the equality for every eigenvalue. Then the eigenvectors of that matrix would constitute a basis for Fn, and this is going to the vector space Fn, and this is going to have an impact, the interesting impact on our next part of the discussion actually. Okay? So let me state the theorem and move towards the diagonalization. Lemma says that suppose you have a square matrix with entries from F, and for this matrix you know, and for all lambda in the spectrum of A, in other words, all eigenvalues of the matrix